Si chiedere se qualcuno di voi con questo. L'hanno trovata ieri, ma sì,
Is this working? Yeah. Okay, so we start the session today first with an announcement. If someone forgot this purse yesterday, please come here or just let us know. Okay, so the first speaker today is Swayamtrupta Panda. He's going to tell us about novel supermassive black hole scaling relations and cosmology from light days to light years. So you have 35 minutes. Yes.
Hello everyone, and I hope you had a great time at the conference day. I'm still reading, you can hear my voice really bad. But yeah, anyways, I'm really grateful for this opportunity. Being here after such a long time, meeting a lot of old faces and new faces. It's really a pleasure to be here among all of you. So, as Emilia mentioned, my name is Swayamtrupta Panda, but most of you know by my last name, Pandas. Yeah. So today I'm going to talk to you a little bit, diving deeper into some new novel scaling relationships that we have been developing with a lot of collaborators here who are amongst us and some who are online and a lot of people around the world. So the idea of this work is going to be trying to explore the AGN structure inside out. So I'm going to first start talking a little bit about relations in the narrow line region, move on to focusing on things about the broad line region. Finally, I'm going to give you a sneak peek of things that we are doing currently with the accretion disk and trying to solve and make use of a lot of the networks of 1 meter class telescopes in the era of Rubin LSST. But before I go any further, I would like to dedicate this talk to Zihuagn. He's been a great inspiration for me personally as well, given that I started my PhD working on island to emission, and he's been a pioneer since the 70s and 80s. He's worked a lot and he laid the groundwork for a lot of observation spectroscopy and see for galaxies, and effectively has worked with many influential people. Like here, this is one of his pioneering work in the optical spectrum of radio galaxies. He's also worked on the 3000 angstrom bump in quasars. We are very well aware of this 3000 bump. In fact, this is one of the key characterization or intermediate redshift AGNs in order to derive the luminosities, get the volumetric luminosity, and effectively measure the black hole masses for objects around the emission pool. Of course, he's also worked on the oxygen 1 line, which is a very common topic here. Deborah, Marilyn, Paula, and all of us are very familiar with this topic of the low ionization broadline region. And this is something which he also worked on back in the 80s. And not to forget, of course, iron to emission. He laid down also the groundworks for the Gaussian diagram for the iron to permitted line, and did a lot of radiative transfer modeling back in the 80s, which have really prospered our understanding to the date. Unfortunately, Steve was also, among being a great researcher, he was also a pioneering tech-savvy person. And this is why, thank you. This is why he was the choice at the National Optical Astronomical Observatory, the NAAO, which is first by NIRSpec, which is right. And he was the Chief Information Officer, and he retired last year. And unfortunately, a month and a half ago, he passed away. So, just want to dedicate this talk. All right, I think this talk I'm going to cover a lot of ground and be really fast on this. We want to miss out on many things. We'll be talking a lot about the global black hole mass scaling relationship that we've been developing in Brazil in collaboration with Rodriguez Sadia, who's going to give a nice overview on this topic. Then I'll move on a little bit about how we're getting ready for LSST as part of the Asian Science Collaboration and one of the full members and leading the task force for Asian Watch List. This is something very dear to my heart. And this is the word that I give with the diesta and the students from polar variability, and we're able to reveal a universal scaling relationship with the energy condition. Something that I work a lot recently, thanks to also Leslie, a really good proponent for this in the changing field agent. We're not only just trying to observe changing field agents, but trying to understand what really characterizes them, especially what's the niche parameter space in order to observe changing field agents going in the future. Also, I'm going to reveal back from my PhD work with a lot of people involved here, the first ever FE2 radius luminosity relationship in the ultraviolet. And I'm going to tell you why that is useful and important in order for us to understand that. And finally, I'm going to reveal this faster, 150 times efficient and faster relationship with the light masses of supermassive black holes, taking advantage of accretion disk relocation. And this is something that my school asked me to do. I'm going to give you also an opportunities that are available with Gemini observatories through the Open Sky program, which is available to each and every scientist around the world. And you can take advantage of this. So I hope we can talk a lot more about that later on. All right, as I said, I'm going to try to do this inside-out approach. We're going to start something talking about the narrow line accretion, move on to the broad line and the accretion. This effectively, of course, we should not forget the spectra is so useful and so important for us, because what we see here at least can be divided into three key components. We have the underlying accretion disk, of course, we're not able to see that visually, but that's something that model approaches and theoretical expectations tell us a lot about and give insight to that. And then we have the emission lines, broad and narrow, giving us the characterization of the velocity profiles, how far or near these lines are, and lets us know about the radiant distribution of the gas around the supermassive. And of course, we are not to forget the absorption lines, which tells us about the full gas medium in between the line of sight of the AGN itself and the distribution. So effectively, looking at the spectra is so useful because it can give you three main characterizations: the geometry, the composition, and the energy. Three things that are very key for our understanding of what happens in the central inner subparsec region around the supermassive. All right, so measuring black hole masses has been, I think, quintessential for every one of us who's involved in AGNs. We really need to know about black hole masses. It was a nice comment by Louis the other day when we were discussing about, we need to get the supermassive black hole because that defines the gravitational potential effect and lets you know about the gravitational system around the black holes. So, briefly, the black hole masses can be divided into three key categories. One is the dynamic method, where you have binary orbital motions around stars, upward motion, stellar velocity dispersions, echo mapping, which is the radiation mapping. Then we go on to the spectral fitting or broadband energy distribution, which is effectively, this is where the culmination of accretion disk and theoretical expectations comes together with the leading data that we have in the multivariate scheme of things. Effectively, this is also important to understand that there is this part in the soft X-ray and hard UV region, which is effectively obscured for us because of the galactic absorption. So we need to also develop models, and this has been a lot of characterization in the last 10 years, where people have been able to pinpoint the theoretical expectation to such an extent that we have been able to characterize that missing part of the problem in the broadband SED modeling. And finally, together, mixing all this together, we have the scaling relationships. So we take the advantages of our understanding of whatever we have been doing with the dynamic methods and with the spectral fitting, and try to combine these together in order to understand and apply it on broader statistics of AGNs. So one key and most long-standing one is the M-sigma relation itself, which most of you are familiar with. And effectively what's happening, even with this kind of distribution, and especially with observations which are now peering into the low luminosity regime, we are actually having a lot of deviation around the low mass, low sigma region of this relation, which is kind of also increasing the intrinsic scatter in the relation that we are seeing. And this intrinsic scatter is something I would like you to keep in mind, because we're going to revisit this intrinsic scatter in a couple of slides. So what's coronal lines? I think the first expectation from this word that people hear is that, oh, something to relate to corona. And this is very true, because indeed our solar corona does have these high energy temperatures and high energies, which can give you the expectations of really forbidden lines, which are of the order of above 100 electrons. So in principle, we do see these kind of emission, like plethora of these emission lines in the AGN spectrum, ranging from the UV, optical, in the X-ray as well, and in the infrared. And being produced by such ionization potential, the requirement of such ionization potential also puts marker onto them to be considered as reliable signatures of the presence of AGNs inside that. Of course, not to forget, there are cases where even shocks can propel such very high ionization emission lines. But this is something people are working on, trying to disentangle in cases how far the AGN can reach in order to produce such copious amounts of coronal lines in many of these AGNs. So effectively, this is one kind of key diagram that is showing a very simplistic version of around the central supermassive black hole. So this is that the accretion discontinuum and provided by the second part of the inverse quantization that is realized by the X-ray report. Now you can see there are a couple of lines that are very important, and this is something will be talked about later by Umberto. So these are the 4 emission lines, which are definitely one of the cases where Fe7 is in the optical, silicon 6, silicon sulfur 8, and silicon 10 are in the near infrared, and effectively have very high ionization potential, a lot more than the low ionization lines that I mentioned before, the island 2. So effectively, you can see that as a characterization of the black hole mass and the accretion rate, which basically determines where is the peak of the accretion discontinuum happening, you can understand that the dependence on mass and accretion rate has a big role to play in telling you which is the main driver behind these high ionization coronal lines. So we took this challenge upon ourselves. We have already a big database of reverberation mapped AGNs where the masses have been determined very quite precisely. And effectively, what we wanted to do is a follow-up in the optical and near infrared to characterize the presence of these coronal lines, first of all. And the understanding was, can we trigger that and link it with the peak temperature of the accretions? Now, why this is important, I'm just going to skip this slide and go here. The temperature of the accretion disk, according to the standard Shakuras-Miyayev disk, is basically proportional to the black hole mass itself and the mass accretion rate, given for a standard efficiency and a truncation in a radius. So if we boil down these first two parameters, the mass and the accretion rate, effectively the temperature can be determined by these two observables. We can get it from different techniques. So coming back, effectively we try to pin this down. So the black hole masses over here are coming from the Benz database from the reverberation mapping. And this is on the x-axis is the ratio silicon 6 over the nearest hydrogen emission line, the bracket gamma wattage. As you can see, these are 21 objects where we have the silicon 6 determination. And already, I'm not going to spoil the relation, Alberto is going to give you a hint on that. The 1 sigma dispersion is of the order 0.44, already comparable. So this has been around 4 to 5 years. And we are already competing with the state-of-the-art M sigma relationship in terms of scattering. Of course, a lot of work needs to be done to expand the mass range now and the accretion rate itself, but this is really promising, and I hope you will all be able to use that in the near future. What's very interesting is the two extreme ends of this. Now, as I mentioned in a couple of slides ago, that the accretion discontinuum really depends on the black hole mass and the accretion rate, right? So effectively, when we're pushing the frontier in the black hole mass, keeping the accretion rate more or less the constant or a little bit lower, the accretion discontinuum shifts towards optical UV, leaving aside the path from the X-ray corona to be dominated, to be the dominant driver behind production of this emission lines, which are these coronal lines. On the other hand, when you move into the other direction, this becomes accretion dominated because now that accretion, same accretion, shifts into the soft X-ray regime and effectively becomes the main proponent to get you the emission line. So there is an interplay between the mass and the accretion rate in order to get you the contestation or the competition between the two components. But we don't stop only on that. And this is something that's very interesting, what I mentioned about the unobservable soft X-ray emission, the warm corona. So what really happens, if you want to understand theoretically what's really happening, is that we have the accretion flow around, which gets heated up to Compton energies, and due to the presence of magnetic flux lines, can create this manifestation of the hot X-ray corona. Now, this hot X-ray corona, most of us are aware of one of the models very famous by Andy Fabian, the lamp-boost corona, effectively, which is quite isotropic in nature, which means part of the radiation can hit back and come back to the accretion disk itself, to the cooler regions, and manifest in what we now call the warm corona. And this is that unobservable part of the warm corona itself. So you have on the solid lines, the two-component SED, the naturally ones that are being used pretty regularly, the accretion disk plus the hot corona. And there in the dotted line, you have the accretion disk the soft X-ray, the one corona, and the hard X-ray corona. Now, what's important to see is how the change in the accretion structure, the SED itself, happens and how it behaves when we go from high black hole mass to low black hole mass, entering into the regime where it goes from X-ray dominated, X-ray corona dominated, into the regime where it becomes accretion dominated. And this is very interesting. I think Alberto is going to give you a little bit more detail about how we made this agreement with the data available on multiple coronal lines, including this theoretical expectation. So effectively, we do pin down that the concentration of the accretion disk has the key driver to play in order to reveal these coronal emission lines and the mass relation that we're getting from the coronal lines. But what's interesting also is the aspect to look into the Eddington ratio aspect, right? So this is the Eddington ratio plot with the same ratio, so it consists of a bracket gamma, and these are all the 21 objects for which we have the near-infrared spectra from JWST and from SOAR and from IITF. Effectively trying to show you that indeed with increasing Eddington ratio, the ratio increases. Something that you might have said by the quasar range sequence diagram, where the ratio of the permitted FE2 emission to the H beta is proportional to the increase in Eddington ratio. But something's amiss, and that amiss is the part where we take into account the low mass narrow line sequence. What happens when we enter this regime of low mass narrow line sequence? You simply don't see coronal lines. They just disappear. And this has been puzzling us a lot, that effectively at that frontier, there is a big dive, and effectively this relation doesn't stay intact when we are receding or we are approaching this XA regime or the extreme accretion regime or the super resolution regime. So this is something of a nature that we would like to explore more, so more work needs to be done. But in any case, we have a much more advanced and updated mass relation that will be revealed in a future time. I would like to take a brief moment here. I know that yesterday's session was all about double peaks and about relations around dual AGNs, binary AGNs. There's something of the sort that we also found serendipitously. This is the first observation of its kind in the near infrared to show double peak emissions in multiple permitted rod emission lines. Oh, sorry. Yeah. Effectively, as you can see, there is oxygen 1 attached to this side from the 8,500 angstrom going up to 2,200, where we have also the bracket gamma. Effectively, we have been able to identify multiple persistent rod emission line, double peak emission line in all these permitted low ionization regime emission lines. And this is very interesting. This is the first of its kind study done in the near infrared. And effectively, we've been able to do this thanks to the work led by a PhD student. Now she's a postdoc at LLA, the Nimara. And we've been able to not only characterize the inclination angle, but thanks to the motivation that these are near infrared lines, we can actually get an expectation of the outer edge of the line emitting accretion disk, which allows us not only to derive the size of the accretion disk itself, but in addition, get the inclination angle to the point in order to derive the black hole masses more efficiently in this case. Of course, we're not still at the point to identify whether these are dual AGNs or these are binary cases. This is something to be studied in the future, but this is something very interesting because of the key importance that the near infrared emission here is much more isolated and it's much easier to model if you want to understand this nature of the binaries and dual AGNs. All right, moving on. So we know that Rubin is coming, and this is something that came up yesterday. We announced that since 23rd October, the operations have begun. This is the last phase operation before we start the actual 10-year campaign, and the current expected date is no earlier than 31st of this year. This was earlier scheduled to be in January, but we're going to expect this happening very, very soon. So really big data is upon us. The DP2 releases in about June. So all of you who are working with variability in the Rubin space, that's very interesting. And if you have more questions, come to me and discuss about that. So a lot of data is coming, a lot of things are happening. Are we prepared for that? And how can we take advantage of this big surge of data from Rubin effectively and be prepared in order to utilize their potential across Redshift? This is something we have been working, and we finished this with the master's student of Paisa, Igor Bunati, and he's co-supervising him. And what we did is take a very nice step back and look at the current most useful survey that's been happening in the ZTF, of course. It's a pity that ZTF is going to shut down probably very soon unless they get extended funding. But what it has been doing in the last couple of decades is been allowing us to get almost nightly to bi-nightly cadence of observations around a big part of the sky. Something that Rubin is just going to do. That's why ZTF is a very clear precursor of what Rubin is going to give us. Now, here I'm showing the overlap of the filters, the GRI, the 3 bands where ZTF performs. And you can also appreciate that as a function of redshift, you have to take this into account. It's not always the continuum that goes into the flux. There is a lot of importance of variable emission line that also triggers the change in the AGNs themselves. So looking at photometry is interesting, but if you want to do a little bit more, you have to understand the underlying emission line features and how to disentangle in a time variable manner. And this is where comes the approach where we are utilizing the Artemis program, the all-quasar multi-epoch spectroscopy. And effectively, this is under the schema of the black hole mapper under the STSF 5. Effectively, what we have is we have 915 quasars in the redshift of 0 to 3. So you're effectively getting all of the broad emission lines in that in the characterization. And we have the DR16 STSS catalog. So we have spectroscopic data available, including mass, luminosity, and VO3 tolerance. So let's go to see what we're getting. So this is the flow chart. That's basically what's happening. We are collecting through force photometry 6-year-long ZTF light curves, and we are deriving this fractional variability metric. So fractional variability metric is the square of the excess variance to the ensemble flux square and square root of that. This is the property which allows us to bring down a robust measure of the intrinsic variability of light curves. And effectively, by using this formalism, we are also able to reduce on the uncertainties and effectively be able to find out no bias due to the introduction of distances of the source. So what's happening is that this is one key example of the long baseline light curves that we have collected from this force photometry pipeline, and that's the information we're getting. So what we did was basically we characterized the fractional variability and pinned down with all the observable spectroscopic parameters, including black hole mass, volumetric luminosity, and of course, not to forget the Eddington ratio. What we are finding is a very interesting thing is the robust anti-correlation between the Eddington ratio and the fractional variability set across redshifts. And of course, you can see that there is this flatter line. This is basically at the weaker relation at the highest redshift where we do want to populate those sources as Rubin picks. And so this is one of the very interesting relation because we're going from variability, imaging variability, into a property that is spectroscopic and determined. So you can actually use and invert this relation to determine black hole masses as well. So we don't stop here. We try to affirm whether this relation is robust as we think it is. So we ended up doing a lot of testing around the light curve baseline length and the number of observations, trying to include more force photometry in the current year, removing host-dominated sources because there's a lot of interpretation, misinterpretation, especially with the Stoneges and Sky Surveys database, where we are limited by the stellar template set. So effectively, we have the host galaxy interpretation only up to the redshift 1, and effectively everything else is just assumed to be no stellar template. So we try to also remove this dependency and try to see whether that destroys our relation. It didn't. We then do quality cuts on the FR, and not only that, we also detect the dependence on the black hole masses, which is shown here. So effectively, as you can see, with a narrow scatter of 0.15 back, the relation is robust even with changing black hole mass from the range 6.5 up to 10.5 in log scale. So overall, this derived reversal is so almost universal. We still want to understand the nature of this, enables prediction of quasar variability from accretion parameters directly, and offering us a powerful tool when we're entering this high cadence surveys. All right, I want all of you to take a moment here. That's a very nice spectra. I really love this spectra. When I was working back in 2022 on changing look AGNs, we were trying to make a catalog. And the idea was, can we have a big sample of homogeneously understood changing look AGNs from which have been vetted from the past? And this is basically the poster child of that work. This has 72 epochs across 15 years, and a lot of reverberation campaign has been done on this object already. And this is fantastic because we are getting information from the emission to line, H beta, and pumping until F5. And you can see all the variation of the emission line across that 72 epochs, spanning over more than 5,500 days. But we have a statistics. We ended up doing actually, the idea was The expectation for changing look has been actually a bit divisive because it depends on the type of codes that they're using to extract the spectral parameters and really what's really happening between one epoch to the other. So we wanted to reanalyze that. So we took that hard work upon us. So effectively, we characterized more than 100 changing look agents back in 2022, which is now really a lot more right now. But there were very key findings that we were one of the first to derive that. So focusing on this one part here is something that has been a lot of expectation because the time scale of turn off AGNs is definitely much more in biasing our sample in comparison to turn on AGNs, given the time scale it takes for the AGN to turn off. This is something that we are also finding in our mixed sample of about 100 AGNs, and it corroborates all the results that effectively when we're tracing the photometric variability, we do see more of this bias of turn off AGNs as compared to turn on. Not only that, we've been able to find patterns in multiple of these AGNs where they are doing periodic or aperiodic turn on, turn off in multiple epochs. Also, because thanks to the multiple epochs, because most of these objects, we have 33 of them, which have more than 8 epochs, which allows us to trace their evolution and transition over this long time scale in boundary treatment versus luminosity plot along the Blackwell mass and Eddington ratio. This is the virial Blackwell mass, so it's not to be confused with the actual Blackwell mass because the virial mass depends on the radius and the velocity dispersion. Effectively, if your line gets stronger, of course, you're going to be a bias of moving Blackwell mass. So this is the virial mass versus the Eddington ratio, and you can see this particular object moved a lot along that sequence. And finally, a very nice correlate to the Blackwell mass and Eddington ratio is the movement on the Kreyszig sequence. The Blackwell mass is very well related to the full width of maximum H beta, and Eddington ratio, as I said, is also quite neatly correlated to this parameter of. I'm not going to be able to talk a lot about Kreyszig sequence. Paula in her talk will introduce us a bit more, but this is crucial to understand the interpopulation transition of these AGNs going from population B radio loud nature to population A. So these changing look not only stay in the same population, but sometimes are able to do interpopulation transition along the period of their movement. So that's very interesting. But the most interesting plot that came out from this analysis is the one over here. This is basically taking the earliest epoch and the latest epoch of all of these changing look agents and showing their Eddington ratio distribution. So that's very interesting because this is not a result that only we find, but of course we were one of the first to do that. But later results by the BUS survey, the STSS, and more recently the DESI survey have reconfirmed that indeed the changing look phenomena happens around that Eddington ratio of 10%. And what's basically driving this Eddington ratio evolution is most likely related to the works that have been led by Nora and Don and Smigosta about driven by the in situ accretion disk transition modulation instability, however you want to call it. And effectively, that is a possible deviation from standard disk paradigm, effectively moving on towards ADAF nature, the adduction dominated accretion flow nature that's been suggested by many of the previous authors. We have the statistics, we have the advantage of statistics, and we have been finding that this parameter space is very crucial if you want to look for changing look agents in the future. But the advantage we also have, we have tons of data, multi-wavelength data, especially for a well-known, very well-known agent that most of us are aware of, NGC 5548, spanning of 43 years of data spectroscopy monitoring. So the advantage with this is that we are able to create multi-wavelength temporal SEDs, which is something that we are lacking at the moment when we want to interpret radiative transfer models with the observations that we're getting. The advantage with this kind of data set is that, of course, we'll never be able to reach 43 years just with Rubin alone. But this is something I would like to propose to people to also look into more temporal epochs of SEDs when they're trying to introduce that into their modeling approaches. And this is very interesting because presence of such long-range data in multi-wavelength allowed us also to reveal a very well-known effect which has been long forgotten, the Kronig-Churayev effect. So back in the 70s and 80s, Kronig and Churayev they found this relation with a lot of AGNs, the well-known reverberation map AGN, that with the increasing incident luminosity, the H beta line luminosity does not go 1-on-1. It starts saturating. Basically, the Strongian sphere saturates, and the H beta luminosity does not grow even with the growth of the continuum. This is very well connected to the phenomena that we are seeing in some of these changing look. And this is something that we can understand better through the analysis of such well-known and well-understood objects if you want to understand what's happening in those very big sample changes in agents where we have maybe 1 or 2, 3 epochs. So this is quite interesting way to understand taking advantage of single object, multi time scale data series in case of this 5548. Now we move on to a bit more closer to the VLR aspects. So this is very well-known technique, the echo mapping, which reveals the structure within the AGN itself. So this is one of the early works done by, reveal that. This is one of the early works that we try to calculate the H beta radius luminosity itself. And you can really see that the scaling relation is not as tight as expected. Effectively, we are able to understand this deviation is actually a function of the accretion rate, and that is characterized by a very key observable parameter, the RFE again, which is key to the quasar sequence. So effectively, what we are doing here, we don't stop there at the H beta. We are also doing an updated Emission to base relation, because with the increasing redshift, this is also very important to analyze higher and higher redshift sources, but also to contest the relations that have been found by big surveys like the SDSS reverberation mapping, which span a very wide range of luminosity, but nonetheless are not able to go to timescales as high as the ones that we are approaching. So with Bojana Cherny, my PhD supervisor back in those days, we started a very big campaign, which is now running on its 17th year on reverberation. And effectively, we are able to anchor the relation. And this expectation tells us the Emission to radius luminosity is much more flattened than the theoretical expectation of 0.5, which is something that the H beta does. And not only that, thanks to this coverage of objects in the Emission to, we've been able to also compile the first ever UV-Fe2 relation. And you may ask why that's important. One, look at the slopes here, much more stronger. So effectively, changes of time delay are happening on longer time scales here. And this is basically the revelation of the stratification in the broadline region itself. So the Emission to UV-Fe2 and the optical Fe2 sitting really back on the scale where it's shielded by the radiation forces from the emissions. Not to forget, I would like to take a moment here. Diego Colipal is a student of ours who is working on Fe3 emission. So stay tuned for his talk later on today. And why this is all important? Why do we care about reverberation mapping? Why do we care about the scaling relationship itself? We want to take it a step further. We want to do the big picture. So effectively, what we were able to do, basically extending from the work from Du and Wang, where, as I said, that scatter disappears when we take something which is not cyclic, because introducing Eddington ratio into this relation was cyclic, because that's the same Eddington ratio used in order to derive the luminosity. The luminosity's effect is going to be a cyclic problem. Now, taking into account a totally independent observable, we're able to scale back the radius luminosity back into that relation. And that's very important for us, because then we have a characterization from radius luminosity and do a single epoch spectroscopy to determine luminosity distances independently with use of two different techniques. That's very useful because we are able to extend to higher redshifts and populate the Hubble diagram using just quasars. And this is quite useful in order to break that problem of the Hubble tension and understand that just using the quasars between the late shoot and the early universe. Not only that, we don't stop here. Of course, I don't have time to go into that, but now we have been able to use quasars independently to determine the Hubble constant. So that's a neat challenge that we have taken upon ourselves. Using intensive accretion-based modeling and spectral energy distribution, we have been able to determine Hubble constant very close to the one of the early universe, 67 kilometers per second per megaparsec. If you have more interest in this topic, please come to me and we can discuss more. Now, finally, into the last phase of talk. Now, we have talked about the BLR, we talked about NLR, what's happening with the very high redshift cases. So effectively, what's happening is that the way we do the reverberation mapping is basically quantifying the change in the emission line relative to the agent continuum. But that's not the only way to do reverberation. There's another one, characterization of the relation to the agent continuum itself. So the underlying accretion, this has a temperature profile which is radius dependent. So effectively, by changing and observing this different chunks of the part of the accretion disk, you can also derive this temperature profile and the size of accretions, which is the underlying continuum that really drives the nature of this. Juan is going to talk a lot more about their intensive campaign that we've carried out. So stay tuned for his talk. Now, with the radius luminosity, when we're doing with the H beta, it usually takes up to a few hundred days, even for the most luminous H-bets. Now, going to the starting 4 days reverberation mapping, it took Shai Pasquale's collaborators a matter of 2 decades in order to build this relation. This was basically published in 2021, and he started this work way back in the early 2000s when I pretty much didn't even start my school. And this tells you the amount of intense work that needed to build this radius luminosity effectively to its current picture. So effectively, at high reaction, we are able to determine and get this radius luminosity relationship. And that's the key problem here. Original grouping campaign runs for 10 years. This is not sufficient enough to build more and populate more of these kind of very high reaction and high luminosity sources. So what do? We devised a very interesting and challenging smart technique. And this is basically trying to understand what's the nature of the underlying accretion disk itself and how it correlates well with the line emitting carbon flow region. So this is basically the schema over here. I'm just going to very briefly go on that. The temperature profile is basically, again, dependent on the mass and the accretion rate. And effectively, by convolving the X-ray driving light curve, which we're producing by our spectra itself, and convolving with the transfer function, we derive the light curves that are in independent wavelength bands. We introduced contaminations very systematically using the PLR emission lines, scattering, the fuse continuum, which is quite important in this work of accretion disk modeling, post-Galaxy and nuclear extinction, and derive eventually the expected time delays between these pairs of bands. This is one of the first works. We were able to publish this, the theory aspect of this last year in APJ letters, and we were able to mix the power of SWAR and LaCie in order to lead to a new discovery. So this is one of the first works where we have taken the challenge to observe the accretion disk for the first time next to the cosmic moon, redshift 2.66. And the effective, and you can see the quality of the light, it is beautiful. You can see micro variability features along the pairs of light curves, and we have the photometric precision on the nucleus flux of the order of 0.2%. And this is amazing because this is also not only the first time we have an accretion disk size and high redshift AGN, but it confirms the standard thinness prediction, especially because we were having a spectra and we have the advantage of using medium band filters on meter class telescopes. That's the important takeaway from this. And finally, this is the relation that we have derived, which basically tells you why the 165 times efficient more faster is the key to go here, that we can effectively have on the boil it down. If it takes 1 year to do the reverberation mapping with standard techniques, it takes of the order of 4 to 5 days, times 2 times the Nyquist frequency. Now, moving on to the very high reaction cases, the 16-year cases will take you up to a matter of 70 days to do the same radius luminosity relationship using the accretion disk, derive the sequel PLR, and derive the Dr. masses for all of these stations. So this is a very useful and powerful technique which takes care of the ground-based meter class telescope in comparison and compatibility with Rubin, however it's going to do in the near future. And very quickly, I'm not going to take a lot of time here, just wanted to briefly lay out. Yes, I will. Yeah, this is the last item. Okay, all right. And the idea of the OpenSky program is not limited just to the partner countries in Gemini. This is a very well-known thing. It's an information that's not really passed upon very well, but it ensures that this process allows everyone in each one, if you have a project in mind, to utilize the capabilities of Gemini observatories. It's ranging from imaging and spectroscopy using low resolution, high resolution, up to 95K resolution. And you have as many ways to apply for time as there are weekdays. So if you have more questions about applying to Gemini time and using for your science cases, please come and talk to me. I'll be happy to take questions now.
Thank you.
So, can you hear me?
Yes. Yeah.
So you showed that the chromoline strength is correlated with both black-hole mass and AUT ratio. Do you have an idea of what's the more important physical parameter? I know those two things are sort of tied together, the selection effects.
So that's a very interesting question. I think I didn't mention this, that we didn't only stop with the accretion rate and black hole masses, we also investigated the spin parameter as well. So effectively what happens is that when we introduce the spin parameter, which is nominally studied from the X-ray emission line fitting of the K alpha, we understand that most of these agents are expected to accrete and spin of a value of 0.8 to 0.9, maximally spinning. When we do that, it also pushes the accretion disk continuum to the soft X-ray regime, which is again going to only tell me that the accretion disk dominated is the part where we're getting copious amount of ionizing flux to drive these coronal lines. Accretion rate definitely plays a role, as we have seen with the standard accretion disk, but we didn't want to stop there. That's why we introduced the warm corona model to see if that breaks the degeneracy, but it only gets it more stronger. The relation just stays more stronger. So it's neatly tied between these two relations of the accretion rate and the black hole mass itself. So, but we would like to do this decoupling, basically somehow trying to understand it through the, modeling using incorporating quasar main sequence in this plane itself, because it's the first time we would be introducing coronal line emission into the context of the eigenvector one. So that's something in work, and I hope I'll be able to review those results soon.
Thank you very much. I was curious about the variance of the rate. Remind me the relation that the people at X-rays demanded and in that case, what we did was power spectrum analysis, and the main picture was the frequency rate. It was taking the relation with the getting rate. And some later on, we found that also obscuration that would be a source of should be. I don't know if you have thought about the comparison between the two, and if you think about that the observation they also.
That's a very nice question. Thanks, Samantha. And actually, with ISA, we are actually working on that right now. So we are trying to get the same work done on the power spectral time space and trying to derive. But of course, as you may be aware, with just optical light curves, it's not really great to characterize both the low frequency and the high frequency end. So really being able to derive the power slope, the 1 over f squared, for example, the time random one, is going to be very challenging just with the ZTF data, which is just spanning 6 years or 6 or 7 years here. But we are indeed able to find the peak frequency there. So it'll be interesting to find how that correlates with all of this. So it's a work in progress with the master students. And yeah, we'll be able to show you something soon. Thanks.
Thank you, Emilia. So I don't know what the title of the PowerPoint game for myself certainly was for me. So this is the actual thing I always talk about. So my name is Emilia Järvelä. I'm at NIRSpec right now, and today I will be telling me about some really extreme high variability we have discovered in the early stage in AGN. And this is part of the project concern. You can see here that I started a few years ago, and if you want to learn more about it, you can head to NLS1 space. That's basically similar to what I will be talking about. So basically, most of these sources happen to be NLS1s, although I think it's probably an observation bias because those are the units we have been actually looking at so far. But anyway, so NLS1s have been mentioned already a few times, so basically they haven't been properly introduced. And let's see if I can introduce them well. Oh, it's a bit difficult or something. So basically, narrow line secret one. So we have type 1 AGN that have narrow, broad, permeate lines. So by definition, NLS1s have a full entanglement HP of less than 2,000 kilometers per second. And we also require C1 to HP to be less than 3, just to make sure we are actually looking at the information. Whether this classification makes any sense is a discussion for another day. I think it maybe doesn't. I would like to aim more physically motivated one in the future, but for now, we are sticking with this. So in addition to these properties, a lot of NLS1s also show really strong iron-2 multiplets in their spectrum, but this feature is not shared with all NLS1s, but a lot of them. So basically, they are very extreme, quite amazing to eigenvector sources. So narrow permeate lines basically leads to low or intermediate black holes. So usually NLS1s have black holes less than 10⁸ solar masses, but they are a lot less luminous as supernovas, meaning that they are accreted by an integration, especially exceeding unity. They are highest density sources, so basically more signals in positive radio source than BMX. In X-rays, we see really strong soft X-rays and also variability. Most NLS ones are hosted in disc-like galaxies, which basically fits with this idea of them being under-Goold or young AGM still evolving. And according to the first radio surveys, most of them seem to be very compact at arcsecond or kilopascal scales, but it was realized in the early 2000s that actually a lot of them show really high bright temperatures and variability in that similar to layers. And in 2009, Fermi was able to detect the first NLS1 X-ray, especially gamma rays, basically proving that these sources are added relatively stages. And here's one example of a source of an NLS1 that actually hosts a radio jet with an extent of about 200 kiloparsecs. And this source was originally classified as radio quiet. So think about that. Anyway, so basically we have an unevolved AGM. These are the lowest mass. We must not probably know, but black holes we know are able to launch relativistic jets. So they are ideal laboratories studying what are the necessary properties and circumstances for AGM to launch any kind of jets. But that's not the only reason why they are interesting. As it turns out, a lot of, or more than half of the AGM JWST has seen in the early universe actually usually classified as NLS ones based on their alignments. So they share a lot of similar properties. I'm going to go over all of them. Here's the whole list. And this kind of makes sense because NLS ones represent this special phase of evolution in the life of AGM, when this undermass black hole is accreting matter very fast. And we think that maybe most AGM go through this kind of phase during their lives. Here's an example of one model NLS1 that shows insanely disturbable tree. So as you can see, the whole line has been basically So at some point we hope to understand the local NLS1 population well enough to actually take some of the information to Margaret and use something we learned here to study the sources that are way harder to observe. So how is any of this related to radio variability? Back when jets and NLS1s were discovered, I was a master's student at the Metsä Radio Observatory in Finland. And we decided that we want to take a look at this source, the Metsä radio telescope. So Metsä has 40-meter small signal telescope observing at 37 kilohertz. It has a really bad sensitivity, which is useful in the sense that we won't be confused by its information or any other sort of radio emission. And so we started observing NLS1s back in 2012. And for a while, we were looking at NLS1s. We used to have jets, but after some time, we were like, okay, this is kind of what we use, like, let's do something else. So we decided to select 2 samples without any kind of radio selection. So one sample was selected based on really dense, large-scale or megaparticle-scale environments, and the other one based on just STDs. A 4 master students went through like 2,000 STDs manually and 50 sources. So no radio selection, but in the end, we ended up detecting 8 out of 66 sources. So that's more than 10% in radio quiet and radio silence, which was kind of amazing. So we thought we had discovered LLAGNS jets. Here's an example of the light curve. The magenta points are representing of a non-jetted NLS1 in the left and one of our radio sources in the right. So as you can see, showing this kind of similar kind of radio variability, we interpret it as flares, also at 37. So what do we want to do next? Of course, to see these jets. So we asked for a follow-up from the JWST. We had 2 epochs from LTQ bands, so 144 to 45 gigahertz. We had VLBA observations at 15 gigahertz to actually see these sources. And also the Orange Valley started monitoring these sources at 15 gigahertz in 2020. And actually, Orange Valley has also detected most of these sources several times. Well, what we found was not what we were expecting to see. So this is a non-simultaneous radio spectrum for one of these sources. As you can see, we have this kind of low slit here, when the spectral index is kind of steep. In this case, it's about minus 0.5. And so it's kind of within super maybe. And then we have this high state here. So overall is here and mixed is here. And the amplitude variability we have between these two states is 3 to 4 orders of magnitude. So by a factor of 1,000 to 10,000, which is insane, especially since we didn't see any digits. We didn't see anything with VRP at 15 points. Yeah, so we also, this didn't really help us trying to figure out what this are, so we also wanted to take a look at their temporal evolution. We used mixed-level detections for this, so basically we just calculated the normal laser statistics, variability, brightness, temperature, Doppler factor, and time scales used with these observations, and the variability, brightness, temperatures, and Doppler factors we find are pretty similar to what we see later, so nothing really extraordinary there, but when we look at time scales, they are actually much shorter. So usually in lasers, we see time scales of maybe weeks or months, but in these sources, we saw time scales of days. So it's another piece of the puzzle, and next we have to try to figure out what to actually write on the paper, figure writing about these sources. And we started from the easiest one, so ruling out what these are not. And here you can see all the things. Basically, we went through one by one, trying to figure out if it could explain our observations. I'm just going to go through all of these. If you want to read more about them, it's all in that paper. It's a really long discussion, but I will concentrate on the viable options, so the only ones that still remain. So the first one is the jet or the jet base. Maybe in this case, interacting with the proton vision pouch for a star. So according to simulations, this causes radio flares that last a few days. It has never been observed yet, but someone has to be the first one, right? Next one is free absorption with moving clouds. So in this case, the covering fraction of the proton region would be very high. We would have a jet, but it will only be visible when you have a gap in the cloud coverage. Nice thing about this is that the timescales can be totally arbitrarily short, but otherwise it requires a lot of fronting, so it's not that fair. And the last one here is magnitude reconnection. So basically, the nice thing about this is that we don't require chills. This can happen in the black hole magnetosphere. The biggest issue is that I'm an observational astronomer, I don't know anything about theory, and so far most theoretical works have concentrated on how this looks at high frequencies, so maybe X-rays and gamma rays. So I need to talk to theoretical people about that option. Things got even more interesting. Some time ago, we wanted to start training at 27 gigahertz. It's this one, so it's a very extreme iron emitter that also shows options with outflows, as we here. Hinting at possible super interaction with this source. After these Metzehovic detections, we started follow-up with the JWST and telescope and SWIFT. And based on a Metzehovic detection at 37 gigahertz, and JWST detection at 33 gigahertz of Ka band, we derive a timescale of more than an hour, about 1 hour. And very good brightness temperature of 10 to 21 Kelvin, and Doppler factor of 60. This doesn't make any sense. I know, I'm just a messenger. So are we also seeing coherent emission in HDM for the first time ever? That would be an easy explanation. These certainly seem to be inverse quantum catastrophe kind of circumstances, but we think we are expecting to see some radio flares in those cases. So we really don't know what's going on. So I think one of the biggest obstacles right now is that we don't have the kind of facilities we need to actually study this kind of behavior in radio. So we would need something with a really short response time, observing at high frequencies, being very sensitive. So maybe we have to wait for edge to get late, hope that it gets funded. The other option is to monitor large patches of the sky and hope we catch one of them. And actually the CMB experiment helped us in this space. So for example, the South telescope, I'm also involved with some could be maybe something like this. A shorter wavelength, I don't know, if the scale is a function of wavelength, maybe we wouldn't be even able to catch these facilities. So long story short, we see insane extreme high frequency variability with two different radio telescopes. So we hope both of those are not broken. We don't know how to explain it. So far, we have seen it only in once, but that's probably because those are the only sources we have looked at, because who would monitor radio quiet service, right? Maybe we should add a bit more. And so we have to probably wait for the next generation instrumentation and facilities to actually figure out what's going on. Meanwhile, Metsähovi is likely going to get a receiver upgrade next year, so it will be able to observe simultaneously at 22, 43, and 86 gigahertz. And it has a radio sensitivity down to about 10 millichansons. So it might be able to help us. But if you have any ideas about what's going on, please come talk to me, email me, whatever. I need all the help. Thank you. Questions? I probably have just as many questions as you do, so.
Thank you.
Is it on?
Yeah, thanks very much. And you're looking at radar things that do often these types of objects, you see excited things as well. But then I was wondering if maybe somehow the data fluency that not be available in logic. Maybe it will be the other interesting thing is that these objects on some of the brightest when it comes to the optical. You see almost nothing. So I was just wondering if
So in this one we also have speed. As you can see, it's not really anything. We do have some new United observations. I mean, during the last 4 days, since it's the only time that I have to time to do it myself, and it shows more variability. But we also have always valid measuring for the same period of time, but I don't have that. But what we are trying to do is to find this variability into other wavelengths and see whatever we are seeing also, manifests in other frequencies. But all in all, there's it might be that the science test is short, and none of the monitoring programs are able to really see that and short in this instead of this.
Thanks, Emilia. So I have a question regarding if you have tried to follow this up in the optical lab, do you see variations of the optical values?
So we do have so you want from space. These differences, it's not showing it here because they're on space. We don't see it. No, but if you radio, for example, there's 1 hour, it's going to be very short. If it's the same.
Quick one, because you didn't talk about this DNA destruction of the jet itself. The reason I was asking about the optical spectra is that we don't
have like radio spectrum. No. Maybe we think about this needs to come with the justification. More questions or comments, suggestions? Yeah.
I think it's that should monitor more sources, not just analyzing the one.
Yes, that's the plan with the receiver, because it's going to have like sensitivity of maybe 10 millichansons or something. So the idea is to look at more radio quiet and radio silent sources and see what we actually see there. Yeah. Yes. Yeah, indeed, you just need your own radio telescope to be able to do that, because otherwise then it's just.
is there anything fine, like
neuroline super groups? I mean, because you're probably basing your unbounded top down spectrum. Like, so how do we like study these at different orientations?
Spectral polarimetry, your opposite.
Yeah.
I think there's like one source or a few sources that seem to be neuronal over twos.
Yeah.
But you need polarimetry for that.
Yeah.
Sorry about that. You can ask me next. Please select any speaker. Yes. Models are information histories and changing BGN strategies. Respect.
Thank you very much. And I want to thank the organizers for their very generous support, without which I wouldn't be able to be here, and that is true for several other students as well. So let's start. As we've already heard, changing of AGN are this really interesting mystery in the AGN world. We have these objects which gain or lose broadline emission over time scales less than a decade normally, but this is often an outer limit set by dual epoch spectroscopy, which is, there's a gap in between and we don't really know what happened. I'm particularly interested in objects which are changing state. So these are objects in which the central engine is changing its accretion rate rather than some sort of changing obscuration. Our biggest challenge in understanding what these things are is that very, very few of them have some sort of resolved spectroscopy through the transition, which we can use to constrain convergence. And because of that, there's sort of a broad set of theories for what's causing these. So one category I like to call disk perturbations. So this includes the tidal structure of stars into the accretion disk. Also things like the tidal structure of a molecular gas cloud on a disk, spiking the accretion rate. We have some sort of Flume transition, so changing the molecular gas available to the accretion disk itself. And we have some sort of disk instability, so anything that'll happen if you leave an accretion disk sitting long enough. And because we don't have much data during the transition, it's very, very challenging to support or rule out some of these. But I would like to argue that salvation lies within the host galaxies of these objects, and we can use these to constrain changing AGN emergence. So over the past few years, works have found that changing AGN like to live in green valley host galaxies, so galaxies that are shutting off their star formation. This has been used to support either that disk perturbation theory, so the idea that these are actually starburst galaxies in which tidal structure events like to occur. Or this is some sort of larger scale change in the molecular gas content of the galaxy, which is also impacting the molecular gas at small scales. This is not a universal finding, but these were sort of the state of the field when I started my PhD a couple of years ago. And so to try and distinguish between these different theories or rule it out, I realized that if we want to understand why these objects are occurring, we need to understand how their host galaxies are coming to the Green Valley, or whether they're there. And so if we wanted to support the idea that changing with AGN are caused by tidal structure events, they should be more likely to occur in galaxies which experience a starburst or an close starburst, as is true for TE host galaxies. And if it is really just some sort of molecular gas change, then we might expect a sort of slower formation time scale. And the only way to get at this is with sort of a resolved star formation history of the kind that you get with stellar multiplication synthesis. So that's what I did. I assembled a sample of just under 40 changing AGN from the literature. I have selected them to be at a redshift less than 0.4 and divided them into two redshift bins just to account for a change in the star formation sequence for redshift. And I've matched them with a control sample of star forming galaxies, as well as type 1 and 2 Sieverts. And we're modeling these with a non-parametric star formation history that's designed to capture the duration and magnitude of a burst, if one occurred, without forcing the star formation history to take starburst. So I'm going to skip over a lot of the methods here because I do want to talk a bit about some more recent work, but if you have questions about the methods, I'm happy to chat that takes up a fair amount of paper. So to get into the results, we find that in our lower redshift bin, changing with AGN star formation rates in the at time of observation are not statistically different from those of other types of AGN. So we do find about a third of them are in the Green Valley, but that's true for the type 1 and 2 systems as well. In the slightly higher redshift universe, higher than 1.5 or 0.15, we find that changing with AGN hosts are a little bit less star forming than the hosts of type 1 Sieverts, but again, they're consistent with those of type 2 Sieverts. Again, about 33% are in the Green Valley. Now, this is very interesting, but like I said, we need that more resolved star formation history to really get a peek at what's happening here. And so to do that, what we have taken a look at here is the median star formation histories across the entire sample. So that's the solid lines here for each sample. And then the shaded regions behind are the 25th to 75th percentiles. As you can see, there's really no signature of a major starburst across the changing mode AGN sample. So we're not seeing a signature that these are super likely to live in post-starburst galaxies. In addition, you don't see any like slow turnoff of the star formation rate at late times when compared to type 1 and 2 Sieverts. And so again, this is not really supporting a sort of large-scale molecular gas transition. But maybe we wouldn't actually catch that starburst. So to test this, we took a look at the host galaxy in Saxon 14 Li. This is a very well-studied tidal disruption event that occurred in the post-starburst galaxy. And so you can see in this pink here, there's a very obvious starburst that occurred back a year ago. And we see a signature of something like that, like one of the changing with the AGN in our sample. I know it looks like there's a few more, but that's just because the lines are overlaid. And so this is not a significant fraction and does not necessarily indicate the type of disruption events are a predominant evidence for constant changing AGN. So the sort of brief conclusion of this first work was that changing with AGN star formation histories were not distinct from those of other AGN, did not look particularly like the star formation histories of TE host galaxies. And so I don't want to say they're ruled out because they're not, but these sort of larger scale molecular gas transition and tidal disruption event pathways seem to be a more minor pathway, if anything, for changing with AGN, and may not be super relevant in causing that changing with AGN transition. And so what other radicals can we go down? Well, it's still possible that changing with AGN are caused by some stochastic accretion events close to the disk, by some sort of perturbation in the disk instabilities, or even small-scale molecular gas transitions that might be expected for such rapid transitions as we see. But again, this lack of observations throughout the transitions really limiting us. We do have those for a couple of objects, but certainly not for the majority of changing location which have been identified. And so for the last few minutes of this, I actually want to talk a little bit about some more recent work looking at disk instabilities as a model for changing AGN. So the key here is really that we can start to distinguish between different mechanisms, different accretion disk instabilities using time. And so if you know the duration of the changing with AGN transition, you can get at things like whether this is occurring over dynamical timescale, the thermal timescale, what kinds of accretion disk instabilities might be occurring that cause changing with AGN transitions. But like I mentioned earlier, for a lot of these objects, we just have a spectrum in the past that looked one way, and a spectrum today that looks a different way, nothing in between, and no sense of how long it took for this transition to occur. And while we can, perform these spectroscopic monitoring campaigns, we can also take advantage of the fact that we have these absolutely wonderful photometric monitoring campaigns with really clean light curves for some changing with AGN. So we can see if we can try and identify the changing with AGN transition inside of AGN variability with something like CTF, or eventually the legacy surveys. So to try to get a handle on this problem, I started by generating synthetic photometry with RubinSim, the Rubin simulation package, which I really encourage everyone to use as we're getting ready for Rubin to start giving out our data alerts. So I took a sample of objects for which I had both the broad and narrow band spectrum in SDSS. And just generated synthetic photometry to see how those changes in the G and R bands might appear in something like a light curve. And additionally, I fit a set of both changing look AGN and damped random walk light curves with a 3-segment piecewise linear fit, just to see whether there was a particular parameter space where changing look AGN transitions stood out. And as you can see here, there is this sort of regime where once you get about a change in the G band magnitude of about 0.4 magnitudes, you really start to rule out, or at least exclude, a vast majority of this sort of normal damped random walk variability. And so actually only about 1% of the damped random walk light curves here do cross this threshold. So we have a very low attenuation rate. And as you can see, we're able to, select for the majority of objects which have been identified in SDSS here. This is likely a bias signal. These were objects that may have been followed up because they brightened. But we do capture this sort of more extreme version of the JWST transition. And so by implementing as well this sort of criterion, change in color, following this bluer or brighter pattern that changing with AGN exhibit, we're able to select a large fraction of the AGN. And so I have some sort of preliminary results here where we're able to identify a changing with AGN transition in about 10% of the objects in our sample. And this is really great considering that for all of the objects in our sample, we have ZTF coverage of about 15% of the time between subsequent changing look spectra, so between the initial state and the final state spectra. So this is actually consistent with greater than 65% completeness. And this is really, really exciting. So we were able to recover the transition for 5 objects and also find candidate transitions for 3 type 1 Seiferts, which may be consistent with normal variability, may indicate a change in transition. And as you can see here, the changes with AGN really do stand out in this sort of variability space in a way that they just really separate from the 2 Seiferts. So that's very comforting to see. And so what you can do is ask how long does that transition take? And again, this is for a small sample. And these are, I should say, observer frame durations. These are not yet confirmed as redshift. But these are durations that are a bit more consistent with something like the thermal timescales. So occurring on timescales of about a year to a few months. And one can imagine in principle, right, doing this for a much larger sample as something like LLAGNS features. So this is, I think, really an exciting new way to probe the increasing disk physics occurring in these changing look AGN, and to try and get at using some of this amazing data that we're going to have through. So to sort of wrap up, changing look AGN, we find that about a third of them live in green valley host galaxies. This is not necessarily distinct from the host galaxies of other types of AGN. The star formation histories of changing look AGN don't show major signatures of starburst or even of slow quenching mechanism, maybe indicative of a Mars transition. They don't seem to be like the TE host galaxies. And hopefully, soon we will be able to put out some work measuring the duration of the changing AGN transition for light curves, allowing us to take advantage of LSST as it comes online mid-year. I have a link to the star information history paper up here since I know I based over a details. And I wanted to recommend the movie Eternal Sunshine of the Spotless Mind, because Zihuagn is supposed to be a place without memory, and this is very much a movie about memory. So thank you very much.
Thanks for the nice one. And I wonder if you have the chance to look at this sort of high variations in the G magnitude are due within small single-digit variation in the G, or there is an important contribution to the emission lines because they get broad.
Yeah, this is continuing variation. So we have specifically chosen a gene subness, the redshift range of 0.2 to 0.4. Because if you do that, the ZTF G band perfectly covers the sort of past that 4,000 angstrom break, and you really get the changes.
Thanks, Margaret. Very nice. So I have a couple of questions. One from the TE aspect. So you are using the ZTF bands. Are you able to also listen language? Because TEs usually have two features. one of the 120, 150 days of the down. So effectively, if you don't see that as a clear-cut state, you also identify where is the time radius happening and what's the muscle. And effectively, where is exactly to be that's muscle. The other thing is, of course, the advantage of uniqueness and having the spectra is the power of physics. So you'll end up also sometimes seeing an excitement of really implying very association. So I was wondering if you would see these kind of pictures in some period review.
So for the second, no, not yet. Although I have not specifically looked at my entire sample, so that's an interesting thing to check. For the first question, I would caution that a lot of the recent simulations of tidal dispersion events in emission disks are very orientation dependent. So I think something like 20S 1927 might be something like a very sort of perpendicular T where you really just have a tidal disruption event on top of something like an AGN light curve. But for some of the simulations of objects which are disrupted a little bit closer to the plane or just deposit material onto the disk, it takes a lot longer for that transition to occur, and you get almost more like that kind of step function that we see in the light curves for the object I showed, which I should have put the name on. It's J1011. It's sort of the large rebellion changing with KGN. So,
quick one on the time of the podcast. It's quite interesting because when you're looking at the changing state AGNs, I would like really interested in seeing how many of them actually follow the diagram. There's been quite a number of changing state AGNs which end up having more resemblance to higher harmonics that harmonic oscillators. Maybe more like this or the where you can have each of the processes in one. Wondering that if all of your expectations that will fit well in the consistency of the changes.
Yeah, some of them do show a change in the variability from a different perspective. I have not looked at whether they are benefit with something like damper oscillators. Since
I think it was funny. Trying to look at this as that people thought that one of the causes might be a changing obscuration. Is it a theory that's probably gone or
I don't think it's gone. And there are certainly objects which are changing obscuration. So the argument I keep seeing is that these X-ray changing with AGN are very likely to be changing obscuration events, which I really did not talk about here. But that's because a cloud in the VLR can pretty easily cover the X-ray corona in a very short amount of time. For a cloud in something like the torus to cover the broadline region, as far as I'm aware, should take much, much longer than the sort of years or months timescales that we're seeing to about a year. And so in the majority of optical changing with AGN, that's sort of the argument that these are likely changing soon. For a number of them, we also have mid-IR coverage where they also get red or low brighter, and it's seen as an indication that this is not changing an obscuration event, but rather a changing state with brightness is changing.
Yeah.
Hello, that was a fantastic talk. So I know that one of the open questions around poststars galaxies is whether when change occurs outside in or inside. And so I was wondering whether your studies of the changing of AGN has shown any support for one scenario over the other, or whether that would be outside.
Yeah, I can't say anything about that. So the essays of spider size, the redshifts I'm exploring is about a kiloparsec. And I don't have any sort of this level spectroscopy. But if you want to talk about some interesting data to do that, we should talk about it. Okay.
One other questions. Let's thank Margaret again. Speaker is Kameron.
Yeah.
And Kameron is telling us about Low-Luminosity GN.
Okay, thanks. Thanks.
Hello, everyone. My name is Kameron Goold. I work with the JWST at the University of Utah, alongside a lot of other collaborators in the LLAGNS collaboration. I wanted to take a second and thank the organizers for putting together this conference and support me attending and giving me the opportunity to be here and sharing our research with all of you. The name of my talk is LLAGNS, where I characterize infrared emission lines in nearby low-luminosity AGN using JWST, NIRSpec, and MIRI IFUs. So low-luminosity AGN, for my work, we define it as an Eddington. So for galaxies that have an Eddington ratio less than or about -3. But they're not just scaled down versions of more luminous AGN. There's a lot of things that happen at these low accretion rates. Your standard optically thick, geometrically thin disk transitions to a radiatively inefficient accretion flow. Low luminosity AGN are often radial loud and host compact jets. The REAF at the inner radii truncate the thin disk, and that leads to a lack of this thermal bump in the UV right here in the ionizing continuum. So high accretion, you get this bump right in the region, which is producing photons high enough energy to excite a gas and leak emission lines. When you get this truncation, you get more of a power law ionizing continuum. Low luminosity AGN are also very interesting because they're the most common AGN in the local universe. Here we have a cumulative distribution. You can see a cumulative distribution of nearby bright galaxies taken from HO 2009. And you can see that there's about 90% of the nearby bright galaxies are accreting at or below this -3 Eddington ratio. So they're nearby. There's lots of them, but they're hard to study because of their name. The brightness of low luminosity AGN is often on par with the brightness of the host galaxy. So JWST is great in this regard because it allows us to spatially separate out the emission from the low luminosity AGN from the host galaxies. We use IFU data to do this. We base nuclear aperture on 75% encircled energy of a point source within 1.2 arc seconds. And here in this plot, what we're showing is a ratio of the emission lines measured within the nuclear aperture over emission lines measured in this 1.2 arc second aperture. And you can see that for the majority of our lines, for the majority of our targets, they are all pretty consistent with this point-like spatial profile, which is kind of designated by this dashed line. The PSF of JWST varies with wavelength, which makes it really fun. So our aperture also changes with wavelength. The shortest wavelengths were about 0.13 arc seconds, up to about 0.61 arc seconds that are longest wavelengths. For physical interpretations, our closest galaxy is M81 and corresponds to about 3 to 11 parsecs. At our furthest galaxy, NGC 1052 corresponds to about 12 to 57 parsecs. So this is our nuclear spectra for all of our targets, including SENA, which was shared with us. We've got the different instruments, important lines, common lines, strong lines that we've observed in our targets are designated here on top. And then molecular hydrogen lines are shown here at the bottom. And there's a lot of common features. There's a lot of differences, but there are some common features, including this silicon emission bump around 10 microns. And then many of our galaxies prominent EAH emissions feature. I have my favorite, your favorite. We get lots of emission lines, about 4 to 5 times the emission lines than what I've been able to find in comparable literature. And this plot just shows the different types of lines that are detected here, from hydrogen recombination, molecular hydrogen, low IP lines like neon-2, argon-2, and higher IP lines listed here, both in NIRSpec and in the MIRI. Some of the most consistent lines that we detected are neon 5 at 14 microns and oxygen 4 at 26 microns. This next slide, I'm just showing our highest simultaneous line profiles for each of our targets. I've just organized them from broad to narrow here. Generally, these are higher mass galaxies further away. These are our lower mass galaxies nearby. M87 has this really interesting double peak profile. It has a blue peak at about negative 450 kilometers per second and a red peak at about 280. This can be consistent with an unresolved ionizing disk, which is in the literature. So that's too surprising. But what I don't think we have a good idea about yet, but maybe can be resolved with modeling, is these low IP lines. So here I'm just plotting things that have an ionization potential less than 23 eV. The red peak is the dominant peak, and then if you go for lines greater than 23 eV, the dominant peak shifts. Some fun little quirk story data. And then I'm listing here all of our full width half max averages for each galaxy. So we're going to use these emission lines to probe the ionizing continuum I was talking about earlier in our low luminosity AGN. Like I was talking about, neon 5 and 04 were detected in all of our targets. And we're actually I plot them here. So neon 5 on the Y and oxygen 4 on the X. Compare them with the literature. All the samples are listed here. And we have the lowest luminosity detections that I can find. With M94 being our lowest luminosity detection. So with detections, these high IP lines, such low luminosities, it's important to be able to identify what the emission mechanism for these lines are. Okay, so you can get shocks or photoionization both create these lines. And so we compare line ratios from our data. Here are the colored points to our comparison data. And then we also compare them with theoretical models here in grids. So the red grid represents a photoionization model that uses a power law ionizing continuum, so no bump. And then the blue grid uses an ionizing continuum that does have this bump. The black grids correspond to shock models from the 3M database, which uses MACNS 5. So here we can see that all of our data, except for NBC 4295, is quite consistent with a power law ionizing continuum, but it's also degenerate with these shock models. And so we've introduced some additional diagnostic lines. Here's neon 5 versus neon 2, plotted against argon 3 versus argon 2. And while still consistent with the ionizing continuum, less consistent with shock models. And then if you expand our suite of diagnostic models to sulfur 4 over sulfur 3, we can see that this shock models just can't explain our ratios in all of these different diagnostics. However, all of our lines are consistent with this photoionization model using an ionizing continuum represented by a power line. We also explore neon 5 ratios against Eddington ratio. So here we're looking at neon 5 versus neon 3 versus neon 2 and versus X-ray luminosities. And in all of these plots, we can see that as the Eddington ratio decreases, these line ratios also decrease, which we interpret as that ionizing continuum becoming deficient in these high energy photons needed to create neon 5 as the accretion rate decreases. I would further explore this by just comparing neon 5 directly with X-ray luminosity. There's a pretty strong linear relationship with our comparison data. Our low luminosity sources preferentially fall underneath this linear line, So we fit a conditional linear model, which basically just splits our data into high and low Eddington bins. The best fit Eddington separation is at negative 3.5. And so then we fit a linear, fit a line to both the high Eddington and low Eddington bins, split at negative 3.5. And this suggests that there's, an order of magnitude difference in neon 5 emission when you get to these lower accretion rates. All right, next I want to talk a little bit about the molecular hydrogen excitation that we see in our targets. We have a lot of purely rotational molecular hydrogen in MIRI. Here, I measure the excitation temperature for transition pairs of the same parity. So in this plot, we're looking at excitation temperature on the y-axis and the different pairs on the x-axis. And so all of our data is plotted here in color. The average is just this red line. And then we also compare this against Lambright's 2019, where they separate out an AGN population and the non-AGN population. And we can see that low luminosity AGN have higher excitation temperatures than both AGN and non-AGN sources. So there's an additional key mechanism that might not be present in these other sources. And this could be from X-rays, cosmic rays, shocks. That's some further work to be done to separate out what's causing this. Okay, so future work would be to, I'm interested in exploring the impacts of kinetic feedback in this sample. Cosmological simulations use kinetic mode feedbacks and explain how they keep star formation off in their simulations. I'd like to measure how energy is deposited across different the molecular and ionized phases in order to constrain this feedback efficiency. I'd love to provide some empirical constraints for feedback models in cosmological and methane simulations if possible. If you're at all interested in low luminosity AGN, there's some cool talks coming up. David Olson has a poster outside today where I look at all the emission lines in low luminosity AGN. David explores the continuum. Yvonne is talking tomorrow about 1058, lots of cool stuff going on there. And then Travis Fisher has a talk about NMC 4258, which should be really interesting. All right, so I recommend to you Butch Cassidy and the Sundance Kid. Paul Newman and Robert Redford are fantastic, but my great great grandpa Ormus Ney was a known associate of these guys and was involved with the last train robbery in Utah. So a little bit of history connected to MIRI. In summary, there's lots of cool emission lines in JWST spectra, low luminosity AGN. It's great. There's a lot of high IP lines, some detected for the first time. Diagnostic line ratios show that it's consistent with the low luminosity AGN emission are consistent with an ionizing source lacking a strong thermal bump. And that weaker neon 5 emission in sources, that there is weaker neon 5 emission in sources with low Eddington ratios. There's also elevated high excitation temperatures in our nuclear spectra, pointing towards some additional molecular hidden channels. Thanks, everybody, appreciate it.
Thanks. So the activity second that is split in the line, that's still unresolved structure too. So yeah, find that basically get information about why we like lower the lines are relationship with the INC.
Yeah, we don't have any real strong idea. The majority of my work is just with nuclear extractive spectra, so I haven't done much spatial mapping of it.
Yeah, you like a lot of or you're just off like where you're running into
100%. Yeah, really excited to explore that. Yeah.
I'm gonna stop. Well, you mentioned that one of the mechanisms or the difference in your is no.
It's not biased. It's not biased.
No, that's no, it's you got your mechanism for difference in the right? So we have and one was X-raying in the emission, was in X-ray related regions. So those things, and why would you not describe the X-ray related regions in the other region?
Yeah, so I think in the nuclear region that we're exploring right now, it's really close to the AGN, so you can still get a lot of X-rays can still be very responsible for the emission that we're seeing in molecular hydrogen. There's a paper over 2010 that gives us a ratio of like H2 luminosity over your X-ray luminosity. And if it's at some threshold, then you can be relatively confident that it's not due to X-ray, X-ray heating. That ratio in all of our targets doesn't rule out X-rays, and so X-rays are. I'm not saying that X-rays aren't responsible for this other, the other targets, the other AGN or non-AGN. Low luminosity AGN also have like a harder X-ray spectra, and so you might just get more of these high affinity X-rays penetrating and exciting molecular hydrogen.
Okay, that's a good question. So which times?
Yeah, so this is neon 2 and argon 2, and then I don't have any good molecular hydrogen lines in M87, but Passion Alpha also shows this stuff peak profile. Oh, yeah, maybe. Yeah, that's awesome.
So, as anticipated, after session, the 10 posters today. While we're downloading some of them, I just want to repeat the announcement. If someone has forgotten this yesterday night, please or tell them I last night. I'm sorry. Did you send the name? No, because we didn't send the name. Anyway. So yeah. Also, see some today in the afterwards. Yeah.
Yeah.
En parte,
pero es más de una slide o sí, para avanzar, para no.
I'm a master student at the Center from MIRI in Mexico City, and I've been working with the variability in the series of the cosmic sequence. So, well, we use the reverberation mapping data, so we have high cadence between 3 days and data since 2015. So, we use the cosmic sequence to select an sample and the index error created by Dr. Swayamtrupta to select only the spectrum with the AGN dominance. And well, I think that the most important thing to say is that we have a lot of future work. For example, we have new data from the new telescope in San Pedro Market, and it is photometric data. So we're excited to have a complete analysis spectrally and photometrically. So, well, if you have any suggestions or comments, I will be pleased to talk to you.
Hi, I'm David Olson from the University of Utah. I work with Neil Sun. There it goes. Rebellion Kameron already set me up pretty well for this, so I can just kind of skip all of this. I work with the same data, but I'm looking at continuum instead of the emission features. There's a lot of contamination from the most galaxy in the infrared, as you can see, which I had to use model independent brightness profile fitting to isolate the point light AGN, which allows us to compare to existing infrared X regulations as well as existing models. And is this forward? Yeah, I also wanted to do the movie. This is Carnival of Souls. It's a Cold War classic. It was filmed and it's kind of quasi set in Salt Lake City, Utah, and inspired and limited. We're inspired to make men limited. So.
Hello, my name is Joe Carpenter. I work at the University of Southampton with Sandra Raymundo. This is what my paper looks like, so if you're interested, you can have a look. It's basically a source study of a changing look AGN ZTF18 Abuanga. It's got some interesting features like 5 detectable broad Balmer lines. It means I've been able to, for the first time in a changing look, do some broad line region diagnostics and also test background mass and everything. And being from Southampton, my film is Titanic, because it departed from Southampton in 1912. You've had 113 years, it's probably a spoiler, but it didn't make it to New York. But the film doesn't really, it's more of a dramatization. It's okay, thank you.
Okay, good morning, everyone. I'm my master's series. I studied the relationship between the Verrico region and the jets on specifically blazers. This is my main 3 results, and I'm going to talk to you about just one. The rest you can see in my poster. The more important one is that we found a 76% of new asymmetry outflow in all the blazers. So, if you want more details, please go to my poster.
is the sample. Hi, my name is Alice. I am from the University of Concepcion in Chile. I'm born with the doctor Emilia Järvelä. This cluster is about my master thesis project. We focus on the optical and MIRI vector study of the LLAGNS. We analyze negative elements observed with fire at the Mayan telescope. We have measurement data from past. We want to do correlation dimensionals. Also, we want to do possible summit for future. We want to we want to do a sample of variables for future gravity class interferometer and the VLT. So thank you. If you want to know more, you can check my poster website.
Hello everyone, my name is Margaret. I'm working now at the University of Concepcion in Chile. So I'm happy to see all of you since I have you around the world. So I was quite nice. Found your country. Well, so this time I'm going to present this poster. So we know that the radio is better, many of these properties, particularly is a better of the organization lines like the calcium 2 in the middle of the optical field. But also there are some correlations, particularly the radio loudness parameter. Yeah, okay. With the regular loudness parameter. So the question is if there is any correlation between all these people, between all these properties, the low ionization strength and the regular loudness parameter. So this is the question that we want to answer. So for this objective, we are using the text sample, that is a sample in the optical and in the infrared. And this time we have included several regular loud sources. So here you can see the redshift and also some of the properties. And well, so in these sources, one thing maybe for you it's important that we have found to find these weird profiles with double peaks. We have to add many components, so maybe they also can be candidates for these double ADMs, one ADMs that we were talking. So if you're interested, you can see the full profiles outside. Well, so the point is that our result is when we include all the properties there. So what we found that our prediction is biased level. So we cannot reproduce the one like in the previous, or they have a lot of sources. So basically, we have a bias. And also, I guess that maybe it's impossible to recover this sample because the error measurements are not observed in low level reviews. But so if you want to know more, I will. Thank you.
Hi, I'm Margaret. I'm a PhD student, supervised by one of the Esteban and Keith Horn, working on reversion of HM accretion flows. So what's wonderful about this have to do with it for the people who are trying to measure the delays, current the fluid changes in different wavelength bands, to try and understand things about the size and the structure of the accretion is. So on my poster, I analyzed a specific HM and GC373. Using optical data from the LCO remote telescope network. I applied one for the traditional constellation methods to find these bands, which tend to find that the accretion is very around the sun and bubbles. But I also apply a technique that has kind of basically been extended to the UV optical, which is the frequency result reversion technique, where we break down the variability to different timescales and measure lags from different Fourier components. So I found that model this frequency spectrum with these combined this and the large mass function models, find that we around a significant fraction would be allowed to be able to reproduce this frequency spectrum. So if you find it interesting, please talk to me or come to my poster. Thank you.
Hey, hello everyone. Thank you for the message here. then I would appreciate I'm from Honduras, and we're from Emilia. The topic is 13, that is the does mission nearly ADN field that so okay, so we want to look here is do a mapping here. So we have templates models that this is template models template in nucleus spectrum and other is for nuclear spectrum. So this is a template model. For example, we have 22 template models. So we want to make a fit with another AGM. So we want to see if this pixel we do a make here of pixel by pixel and see if the spectra of this pixel resembles or looks like the circular or nuclear model. So we make these resulting maps of circular or nuclear emission, and we find here that in these 3 AGMs, sector 2 AGMs, that we have some structure here that, for example, this color here is just given by the AGM, and the red here is just given by other mechanism. But the important thing here is that we have a standard loss property beyond the nucleus or beyond the torus. So these results support the idea of those models. So maybe the AGN is not just a torus, but it's maybe a function of those things, but we need more investigation about maybe maps of velocity and map of circles to find something more real. So the picture for this experiment is maybe have a larger samples of the telescope and change this methodology to see what happens in this experimentation. Thank you.
Hi, I'm Margaret. I'm currently a PhD student at Penn State, and I work mainly with microgalaxies. And the main feature takeaway is that we have developed a pipeline that takes the specific geometry of the broadline region, whereas to me it is in a disk-like configuration. As seen in our figure on the left, it's sort of an extension of that hot interfacial disk with brownish lines, which is the formative skin of that disk. And from there, we can input any light curve, empirical or light curve template. One example that I showed here is the light curve from NGC 5538. And with certain choices of emissivity patterns that we can overlay on the broadline region, as seen here, we've been able to inspire or other features. We can then integrate over the fairness and produce synthetic emission profiles. So in the purpose of this light, we've actually developed the H alpha broad emission light. And with this, we can essentially go through a time series and measure different variability in the shape parameters of these profiles. So if you'd like to learn more about how we develop this pipeline and our initial science results, please talk to me. Yes. Obviously,
Hi everyone. Okay, this is my postdoc. This is going to be really quick. I am a postdoc at Vietnam, and I am working with the second deepest X-ray field observed by SMBH. And I am working as a member of the Low-Luminosity collaboration. And basically, what we are doing is analyzing the X-ray observation of one of the best part of the sky to do this analysis because we have the lowest density region on the sky.
In this part, we have 18 X-ray observation, and we are making a stacking analysis and a spectral stacking analysis of all of the sources observed in this part. We are cross-correlated with Herschel observation in far infrared emission, and we have a spectroscopic optical follow-up with Osiris and GBC telescope. With all of this information, we are obtaining some interesting results. For example, we have detected around 10 subject sets, sources, AGNs, all of them. We have around 100 AGN, and at the moment we have identified like high compounded sources as well, which are those with really high column density and in the nucleus. And well, we are working with some other interesting analysis because we have this huge collaboration. And for example, Martin here yesterday presented some results of the energy spectral distribution, and we are using that data to compare the parameters of the tables with some properties of the AGNs. So if you have if you want to know something more about this work, you are welcome to go to my poster outside here, and thank you so much. Okay.